Yesterday we went through chapters 12, 13, and 14. And so now we'll go review some of the other chapters. I'll start off with chapter 15. So 15 was when we got back into fun with carbonyls. Was this 15 or was it 16? 15. Well, whenever we got back to fun with carbonyls. So just a quick review. What happens when we take an aldehyde and then a phosphorus illet? What reaction is that going to be? Dividing. And so what's going to happen if we just have the CH2 on our carbon? What's going to happen to the oxygen? It's going to be replaced with CH2, right? So in the dividing reaction, the oxygen in the aldehyde is replaced by the substitution on the carbon in the phosphorus illet. Yes?
Is there a way you can turn these lights on in the middle?
Oh, yeah.
Thanks.
So what we would get would be the terminal double bond in this case. Alright, what reagent is this aluminum with the two isobutyl groups? It's dibond. What's special with dibond? It only adds once. So if you take an ester and you add in dibond, most likely the product you will get will be the aldehyde. So dibond only adds it once. What happens when you get a ketone or an aldehyde and a diol under acidic conditions? Or if it's a protecting group, what's the product going to look like? What functional group are we going to get out? So a dialcohol, HCl, and an aldehyde. What is an alcohol going to do to an aldehyde or a ketone under acidic conditions? So first off, under acidic conditions, our carbonyl will be protonated. And then the alcohol can add in the protonated carbonyl. Give us a tetrahedral intermediate. Then, of course, in chemistry like this, proton transfer is going to happen all the time, and any number of proton transfers can happen, but the thing to remember is, think of the productive pathway to get the product. Proton transfers are reversible, so a million different ones can happen, but think of the productive pathway. Yes? This guy right here? Yeah. So we will have a proton transfer. We grab this proton. It can go a number of different places, but for a reductive pathway, we want it to go in the OH group, so it can be a good leaving group. All right, so now water under acidic conditions, water can leave. And I think there should be a methyl group. Of course, the methyl group is completely inconsequential, which is why I forgot to draw it, but just to be consistent. So that will give us something like this. And now, since we have this oxonium again, what's more likely to happen? Another equivalent of this alcohol to add in, or this alcohol that's already tethered to it to add in? The tethered one. Intramolecular every single time. So add in. to give us a compound like this, and then we have a proton transfer. In this case, it's probably going to be a intermolecular proton transfer, so one of the water molecules from the HCl, or another proton of alcohol. Something's going to take the proton. I'm just going to draw H2O, or the alcohol could do it as well. To give us our product. Like so. So here's my question for you. So this reaction is completely in equilibrium. And a million other things can happen, but this ends up being the more thermodynamic product, and it happens. Do you think under these conditions with this aldehyde, we can form an enol transiently that then just goes back? Absolutely no reason. So based on that, I drew this as starting from something with a single stereoisomer to something that still is a single stereoisomer. Is this correct? Or do you think this chiral center will be now racemic? It will be racemic, right? Because we will form, under these conditions, we can easily transiently form the enol, and the enol is going to kill any stereochemistry adjacent to the carbonyl. So in reality, you just want to draw it as a squiggly line for racemic. Yeah.
That drawing, that's very right side. Could you just have the oxygen attack instead of the next step? That oxygen.
So you mean this one?
No, the one.
This one?
No, yeah. Can't just get that.
You probably want to go to the carbonyl.
Yeah.
Because what you're proposing would be almost like an SN2 way kicking off the H2O.
Yes.
And so that would be an SN2 on a secondary substrate. Most people just, and I think it's probably more correct, if anything, under acidic conditions, this would be more of an SN1, right? So you would expect this water to just leave. And so if you had the water leave to give the carbocation, maybe you could have it attack the carbocation directly, but you don't want to actually do an SN1 type displacement. You'd want to do an SN2 type of displacement, you want to do an SN1 type, where the water leaves first to give the carbocation. Most likely, though, the carbocation would leave heavily assisted by these lone braided electrons and the oxygen kicking off the water. So it's probably best to draw it to the carbonyl cation. Yes?
Can you explain this for that one more time?
Proton transfer. We want to have water leave. And with proton transfers, there can be a million different proton transfers, but we want to think of the projective pathway. And in this case, we know we want this leave. Since we know this will be the product, we want this water to leave, not this one. And so we need a proton transfer where the proton goes here. It's a pKa neutral event, right? You go from a hydronium to a hydronium. So it's happening irreversibly. And so it's just a proton going from here to here, allowing us to kick off water, eventually giving us this stable 5-membered ring as a thermodynamic product. Okay? So if you see a diol and acid and a carbonyl, it's going to give you this cyclic acetal. This one has something. And so then the other key concept from this chapter was very mechanistically similar to this canonical acetal mechanism, except instead of an oxygen, like an alcohol, we had an amine. So I'm just going to draw a nothing special amine. It will be a little bit different because I have an oxygen, but that's not going to really change anything. It's a substituent. Oh wait, so under Calig H3O conditions and a primary amine, what will the product be? What will we replace the oxygen with? With the nitrogen. And so the mechanism of this, again, will be protonation of the carbonyl. followed by reversible addition of the amine into the carbonyl. Again, it gives us a tetrahedral intermediate that's very, very similar to an acetal. That will give us this ammonium intermediate. So the next thing we can do is we have a proton transfer. And I want you guys to tell me if this proton transfer is a good pKa event or a bad pKa event. So the next proton transfer will be this alcohol-like molecule taking the proton from the amine. Thanks. All right, so it is bad. Why do you think it may happen to some degree?
Right there.
Oh, it's right there. You know, we're also, catalytic H3O, we're also pretty much swimming with water in H3O. But the reason why is kind of a productive pathway. So yes, this equilibrium is going to definitely favor the ammonium product. However, if we form a little bit of this, we have water, which is a really, really great leaving group. So whereas this equilibrium is lousy, we can now, with the high energy lone pair of electrons and the less electronegative nitrogen, kick off water. So kick off water to give us now our aminium. All right, and so whereas this equilibrium is lousy, it gives us a very reactive intermediate that can quickly kick off to give us a more stable product, which then can depronate the aminium to give us the amine. So whereas there's one bad pKa step here, it's Le Chatelier's takes over, because once we form this intermediate, which is going to be the disfavored intermediate, it's going to quickly break down to give us this. So as soon as we form this, it's going to go to the aminium. And that's going to change the balance of this equilibrium a la Le Chatelier's theorem, causing eventually all of this to funnel through the less favored intermediate, pKa-wise, because Le Chatelier's takes over and this quickly falls down to the aminium. Yes?
Why is that a bad pKa then?
Alright, so what's the pKa of this? But roughly 16, right? What's the pKa of this? 0, right? So we're going from, under acidic conditions, we're going to something, or we can even say this is a pKa of 10, this is a pKa of 16, of 0. Regardless, we're going from a more stable intermediate to a less stable intermediate based on pKa, right? And all equilibriums they have to lie to some degree on the towards the more stable thing. And so when we talk about acyl substitutions in a few minutes, we'll revisit that. But again, it's just, pKa's can tell us whether an equilibrium is good or bad. And so when you go to something under acidic conditions that's more acidic, that's going to be more uphill. And if you go under basic conditions, you go to something that's more basic. So in generally, if by pKa's, if you go to something that's less stable, that's going to be a thermodynamically unfavored event. And you can do a rough idea based on comparing pKa's between an equilibrium. So the most acidic proton here has a pKa of 10. So the ammonium, pKa of 10. And this intermediate, the most acidic proton has a pKa of 0. So we're going 10 orders of magnitude less stable. And when you think about thermodynamic equilibrium, it's really what's more stable? And so since we go to a more acidic proton here, it's going to be less stable. However, since this is less stable, it's more reactive. And so it can go back here, or this can fall off to give us the more stable amine. What happens? What would we get if we use the secondary amine?
Don't fall down.
Exactly. So if we use, I'll do this in orange. If you use a secondary amine under the same conditions, do the same mechanism, we would eventually form the iminium. However, whereas with this amine, you can give a proton we can take off to give us a neutral compound. In this case, the nitrogen does not have an acidic proton, so we can't do that. However, these protons, since they're adjacent to the iminium, they're a lot like an alpha carbonyl, right? Hydrogens adjacent to carbonyls are more acidic. And so these hydrogens, which are adjacent to this carbonyl-like species, are going to be more acidic. And not only that, but this is a positively charged nitrogen, so that's going to make them even more acidic. So then the water, it's just going to grab one of the protons to give us what we call an enamine, where the double bond is now between a carbon-carbon double bond. Reactivity-wise, yes?
Should that initial secondary amine have an H on it?
Yes, you're right. That's actually funny because on the last semester's final, I had a question like this, and the hydrogen didn't make it either for the same reason. Usually, our chem drawing software has really good proofreading things that will point that out. But if you forget to fix it, it won't fix it automatically. But yes, there should have been hydrogen. So these react like enols, all right? So if you ever see a mechanism where that looks like it was an enolate chemistry, but the only base provided was a secondary amine, it probably doesn't go through general enolate chemistry. It probably goes through the formation of an enamine, which then acts as an enol and hydrolyzes. So just to give you an example of that, looking ahead to a future chapter. So this is just a Michael addition. Of course, this is a Michael addition that could probably do a Robinson annulation, but let's not worry about that now. So if I were to give you this Michael addition on an exam, how would you draw the mechanism for it? You know, this means not nearly basic enough to deprotonate this, but what it can do, and furthermore, just to make it even more interesting, you can do this chemistry with catalytic amine and catalytic acid. So only like 10% amine or even 5% amine would still catalyze this reaction. And so how would you do that? The only base we're giving you, first is under acidic conditions with catalytic amine, so that's kind of strange. So what's going on? Well, mechanistically, first thing we do is we form this enamine. Through the mechanism we just discussed. So we form the enamine. Enamines react like enols. In fact, enamines are more reactive than enols. So then the enamine Gonna do a 1,4 addition. Do a 1,4 microtype addition to give us the resulting enolate. Well, if you have catalytic H3O, that means there's water, so you can eventually get the resulting enolate here back just to the neutral detail, just so it's easier to draw. And this should still be a methyl group, not an O-methyl. All right. But now, from this enemy doing the attack, it gives us an iminium. And then iminiums, under catalytic H3O conditions, meaning there's also some water around, can then be hydrolyzed back to the carbonyl, initially by attack of the water into the iminium. So now, is a proton transfer from this species to the amine taking a proton, is that pKa favorable? Absolutely, right? So if we wanted to if we wanted to do something like this, it's very reasonable to say, now this proton transfer is very favorable because we're going from, again, molecule with the lowest pKa hydrogen being 0, hydronium, to now a molecule where the lowest pKa hydrogen is ammonium, so a pKa of 10. So now we're going to a more stable system than a less stable based on pKa's. And so remember, all this chemistry is incredibly reversible. So in this case, we can go back to here, and I'm going to call all this stuff an R group, just to save space. And then eventually this alcohol can kick off the ammonium, giving us a protonated carbonyl. With the Michael products, again denoted as an R group. And then we can, through whatever system, have the water or the amine grab this proton to give us our product. Which is this guy right here. So, be aware of stuff like this. I've said several times in class, amines behave like enols. And so if you can form an amine, you can do any of the chemistry an enol can do. But of course, you need a secondary amine for this. All right, let's talk about some nucleic. Yes?
Is this supposed to be a minus somewhere?
What do you mean here, or? Well, I just had, protonating the resulting enolate, just go to neutral species. Sorry, I only mentioned it for like 5 seconds. I was very quick and hand-wavy about it. But yeah, no, I just had to go to neutral species just because it was easier driving around, or, we're under particularly acidic conditions. So anything like this minus charge isn't going to survive there as long as it's being quickly protonated. Alright, so we take a carboxylic acid, SOCl2. SOCl2, yep. SOCl2 and BCM, what product will we get out? Acid chlorides. So SOCl2 plus a carboxylic acid will give us an acid chloride. So what do we know about acid chlorides?
Very reactive.
They're the most reactive carboxylic acid derivative we can get. Meaning, if you can think of it, you can add it into an acid chloride and the equilibrium will favor the product where it's being added in. Someone give me a nucleophile when we talk about in this class for acyl substitutions. We talked about 4 or 5 of them. What? Alright, so that's an electrophile we can make. And so what would the corresponding nucleophile that we would use to make an anhydride from this? Acetate, good. So acetate would add in, give us a tetrahedral intermediate, which would quickly collapse, kicking off Cl minus, giving us our anhydride plus Cl minus. So which one of these sides of this equilibrium would be favored? The right side, right? So remember, with an equilibrium, technically both sides of the product can be the product. So don't forget that. I can draw an equilibrium any way, and so the question is which side is saying the product's more favored? Well, by definition, but that's a very vague answer that doesn't really say it. So you want to say the right or the left, or you want to circle it. So in this case, it's the you're right. So when you look at the equilibrium, there's a few ways. If I give you an equilibrium in exam 3, there's a few ways to look at it. The key is you want to stay consistent. So the first way is you want to look at what's swimming around. So you would compare the acetate and the Cl minus. And you know from the pKa charts I provided, acetate has a pKa of roughly 4, whereas Cl minus has a pKa of roughly minus 6 or 7. So from these pKa's, when you try to assess an equilibrium, and you want to say based on the nucleophilic species swimming around each side, the equilibrium is going to favor the side where the weaker base, i.e. the molecule that's a stronger, whose conjugate acid is stronger. So the equilibrium is going to favor the side where the weaker base or stronger conjugate acid is swimming around. So in that case, that will be Cl minus. So when you're talking about what's swimming around, stay consistent, make sure you're swimming around, and do the pKa. So as long as you stay consistent, it's pretty clear that it's going to favor this by 11 orders of magnitude. So you just take the difference of this, so 4 and minus 7, so that's a 11 orders of magnitude difference. And you know it's going to favor the right side. So we can say that the KEQ for this reaction is roughly 10 to the 11th. Whereas if I reverse these, I put this here and this here, then what would the KEQ be? 10 to the minus 11th. The other way you can assess this, again, is staying consistent, is you just compare now what's bound to the acyl group. It's going to give you the exact same numbers, but now you want it so that the stronger nucleophile or the stronger base is bound to the acyl group. And you do the same analysis, minus 7 -4. But in this case, the equilibrium is going to lie on the side of a stronger nucleophile forming the bond. So either of these analyses are perfectly valid, comparing what's bound, knowing you want the stronger base bound, now bonded to the acyl group, or comparing what's swimming around. Either one's valid, either one will give you the right answer. It's just you have to realize that it switches in that you want the stronger base forming a bond and the weaker base swimming around. And that's how you can kind of say basically the equilibrium is. Stronger base, power to the acyl group, weaker base now swimming around as a leaving group. Sorry about squeaking. Can everyone see this? It's kind of a weak blue. But if we have a methyl ester and sodium hydroxide, where is the equilibrium going to lie? It's going to lie to the right, which pKa's would not tell you. pKa's could say it's going to be in the middle, but we know at this point equilibrium is going to favor the carboxylic acid. Why? Thank you. Because the second we form the acid under these basic conditions, another equivalent of the sodium hydroxide is going to grab the proton, giving us our carboxylate. And our carboxylate is going to be unreactive under these conditions because the carboxylate has a minus charge in the oxygen donating into the carbonyl system, making it much less electrophilic than a methyl ester. So you have this minus charge donating into pi star overload the carbonyl, making it much less accessible by a nucleophile. And so this equilibrium, which is going to be massive, right? Sodium hydroxide is going to have pK of 16. Carboxylic acid is a pK of 4. So that's going to be pushing this basically by 12 orders of magnitude towards this. So this deprotonation does two things. One, it gives it a pKa sink to drive the equilibrium towards the product, and it makes this, in general, just less reactive towards the thing, so it can't do a nucleophilic acyl substitution. So it really pushes the equilibrium towards the carboxylic acid, so much so that it's kind of like honey badger that, we're trying to kick off methanol, yet we'll do this reaction in methanol as a solvent and it will still work great because pKa is not there. It's got this driving force. So you can run this in, sorry, I know the honey badger reference is a little bit dated. I think it came out when I was in college maybe. But nonetheless, this pKa driving force allows you to do the reaction even under conditions where you thought Le Chatelier might disagree, right? Because if you have tons of methanol, you would expect the system to less likely want to give up methanol. But that's okay because we have this pKa driving force giving us the carboxylic acid. Now it's now fun with equalates. So if I take some kind of ketone or aldehyde that has some alpha hydrogens, throw in some H3O, some Cl2, only one equivalent of Cl2, what will the product be? we will replace one of the hydrogens with a Cl. And this will occur through the enol. So, under these conditions, we can transiently protonate the carbonyl. And now, since this is a carbonyl deposit of charge, these hydrogens adjacent are going to be even more acidic than they were before. So water can grab the proton, giving us our enol. Go this way. And we know that enols are reactive towards electrophiles like Cl2. Give us a product like this. And then we can just deprotonate our carbonyl from the, endogenous water in the system to give us our monochlorinated product. We can also do this through a basic mechanism, right? Through the enolate rather than the enol. What would happen if under a basic condition we use 3 equivalents or excess Cl2 under basic conditions? Yeah, exactly. We would trichlorinate it, and then the base would, so I'm just compressing arrows. So if you use excess Cl2, we would trichlorinate this, and now these trichloromethyl groups are actually good leaving groups now. This resulting anion is going to have a pKa not that different than an alcohol, for instance. So if we were to take a base like KOH, it could add in. Kick out the CCl3, giving us a carboxylic acid plus CCl3 minus. And what's the CCl3 minus going to do to the carboxylic acid? It's going to deprotonate it. And what's that deprotonation going to do? Drive the equilibrium to the product. So it will grab the proton, and that will give us our product. Yeah?
Would it be okay if the Cl minus does not protonating instead of the H2O?
So what's going to be more basic? Cl minus or H2O? H2O, right? H2O's conjugate acid has a pKa of 0. Cl's conjugate acid has a pKa of minus 7. So it's probably a little better to have the water do it. So then, first, let me draw a non-symmetrical ketone. What base would we use to get the less substituted enolate from a non-symmetrical ketone? Aldehyde. What base would we use to get the more substituted enolate. Sodium methoxide, yeah, a weaker base. Again, kinetic thermodynamic situation. And then enolates can do any number of reactions. They can react with electrophiles, alkyl iodides, and SN2 type mechanism, Cl2, Br2, in the chemistry we just discussed over there. They can obviously react with carbonyls, but we'll hopefully talk about that very shortly before the class ends, and so on and so forth. So, in a system like this, only one of the alpha carbons has acidic protons. So this is a rigidified system, so it can't rotate bonds, and so the hydrogens are stuck where they are. So which one of these carbons is going to have the acidic hydrogens, which one will not have the acidic hydrogens? Yeah, so this one will have the acidic hydrogens, and the reason being is because if you look at, in order for the protons to be acidic, their conjugate anion has to be able to resonate into the pi star orbital of the carbonyl. If the conjugate anion cannot resonate in the pi star orbital of the carbonyl, it has no stability, and it might as well just be a typical sp3 carbon. So in this case, these hydrogens, as you draw, are roughly adjacent in parallel with the pi star orbital. Whereas this hydrogen, which has Tron, is actually in the same plane as the carbonyl. If a hydrogen is in the same plane as the carbonyl, what does that mean? that there's no overlap, because we know pi systems are orthogonal to the plane of the bond, right? Pi systems are orthogonal to the plane of the bond. So if you're a hydrogen in the plane with the bond, that means it will be orthogonal by definition to the pi systems. So the pi systems will be orthogonal to you as well as the bond. So this hydrogen is not acidic because it's in the same plane as the carbonyl and thus orthogonal to the pi star system. So if you were to make the resultant anion, it would not be able to resonate. You would have a system where the lone pair of electrons would be roughly at a 90 degree angle to the low energy pi star orbital it donates to. And so your 90-degree angle you get donate, you don't have resonance, you don't have the stabilization. So remember, in cases like this, try to ask yourself, and if I give you a case like this, it will probably be this case, realize some hydrogens, not all alpha hydrogens are created equally. You need to think of orbital overlap. Or is it some hydrogens are created more equal than others? So, the less stuff we talked about before the third exam was then getting into chapter 19, which was addition of enolates or enols or enemies into various other carbonyls. The first reaction we talked about was the addition of an enolate into an ester. And this was what we called the Claisen. Where the enolate adds into the ester, kicking off the ester oxygen substitution. In very, very reversible chemistry, to give us molecules like this, plus the ester substitution kicking off. So the ester substitution can easily add back into the carbonyl and give us the reverse reaction, giving us starting materials again, and that's the retroclaisen. And remember, whenever you're talking about a claisen, there's always the distinct possibility of the retroclaisen. All right, the reason the claisen actually works, though, and I'll do it in green, because I haven't used green today, I don't think, is when you have a hydrogen that's adjacent to two carbonyls, that you get in most Clayson products, it's a really acidic hydrogen. So rather than add back into the carbonyl and give us our starting materials, it can easily just snatch the proton to give us an enolate. And just like in the esterification case we talked about going from a methyl ester to a carboxylic acid via the carboxylate to drive equilibrium, this deprotonation drives equilibrium towards the product, or at least towards one product that's got the acidic hydrogen. And so as we know from several examples, if you can't do this deprotonation, then the chemistry is not going to work very well. Or if you have a Clayson product that doesn't have an acidic proton and you heat it up in methanol and base, it's just going to go to another Clayson product that does. Yes?
Why do you choose to do the bonds on that side rather than this?
No reason. Either one's equally valid. You could say that this ester may have a subtle effect favoring this over the other, but there's no reason. Either one's fine. And so then after that, we talked about the aldol reaction. Aldol reaction, again, is rather than adding to an ester, it's a ketone or aldehyde adding to another ketone or aldehyde. And so the aldol, you have to be a little bit careful because you can get two possible products. You can get your aldol product, which is an alcohol. But then depending on whether you use acidic or basic conditions, there are various mechanisms where we can actually now dehydrate the alcohol to give us an alpha beta unsaturated step. Usually you have to heat this up to do the dehydration. All right, so you have the aldol product and the dehydration product depending on if you use heat or not. And you can do the aldol under acidic or basic conditions. And it's the dehydrated product which is going to be more thermodynamically stable. So if you heat it, they'll go towards this. And then that's about where we ended for exam 3. Then everything else we've talked about since exam 3. I'll be more than willing to go through that stuff in detail in my office hours, whether it's directly after this class or on Friday between 9:30 and 12. So